the delay. So let's get started. I'm going to hang out from the teleconference. I don't think so anybody's there. And let's see if there are any questions before we start today. So you're able to see the screen. I'm recording. And so we're good. Okay, so good evening to everyone. And let me just review where we are and what's the plan for the remainder of the semester. So I was just taking some note. So today is 21st November. So today we're going to review the solution for homework 5 to start with. Then we're going to look at behind some theory of how the linear modeling time series data can be done using the LIMMA package. So I will not do the lab today, but I have some slides to take you through. So you need to understand what is a design matrix, what is a contrast matrix. So as long as those two concepts are clear to you, maybe on 28th November, then we can do a lab with the sample data. I originally intended also to do the homework 6 review on 28th November, but I think I extended by a few days because some of you wanted to have that extension because of Thanksgiving that's coming. So happy Thanksgiving to everyone next week. Hope we all enjoy that. Then on 4th December, I'm planning to review the solution of homework 6. Then I may cover the topic of connectivity map and drug signature. And then at the very end of 11th December, I need to review the solution for homework 7, which has to do with time series data, which I will post tomorrow along with lecture 11. So my final lecture on 11th December, I would like to review the solution of homework 7. Because I'm extending the timeline for homework 6, some of these things are actually getting offset by a week, but we'll try to do what we can. And then Group O actually has proposed 19th December as their project review time. So I would want to make it mandatory that all of you attend these sessions. And if you cannot, you have to let me know. And then you also have to acknowledge that you have seen the web sessions if you are unable to attend live during the presentation. I would like to hear from Group J or Y. Ideally, I would like to see that one of you pick the spot 11th December and the other group picks the spot of 19th December, because I'm thinking it's not going to take more than an hour to go through the presentation. And then maybe we can have half an hour for question, answer, etc. So if one of you please do that on 11th December, then the other group can start on 11th December or maybe do it together on 19th December. But I don't want to do anything beyond 19th December because I'm pretty sure you all want to receive your grade before Christmas and we need to wrap up the semester. So this should be the cutoff date, the last time that we will meet for this semester on 19th December. And so I will try to send an email based on where we are and what's the remainder of the activities done. So Group J or Y, please schedule a dim meeting or however way you want to share your screen and present your PowerPoint to take us through your project and through your code. So as soon as you can get into our calendar, that'll be appreciated, and you have to get everyone's calendar. Those of you who cannot attend these meetings, as I said, I want you to acknowledge through that you have received the recording and you have reviewed it, and if you have questions you can ask each other. So it should be fun, and this is the only last 2 times we will meet, so try to attend. So that's that. So that's where we are, and I'm not sure whether there is any question. If not, then let's proceed reviewing the homework 5 for hypergeometric test. So I'll come back to my Excel in a bit. So let me hide that. So on the first half of today's lecture, let's review the homework solution. Then we have to go through some theory to understand linear modeling and LIMMA package. Okay, so what was homework 5? So homework 5, we started by asking that you get your data set, the same one as you did on assignment 2 or the lean and obese diabetic files. So there should be 10 of them. So you have your data. Then we have never used VSN normalization, which is variance stabilization normalization. And I think chapter 5 on your bioconductor case study uses this technique. So instead of RMA, or mass 5, we wanted you to do the VSN for the normalization, and then you can still summarize and report by RMA. Then for non-specific filtering, I wanted you guys to do our row as SDS, not IQR. One thing that was very important, that you had to get rid of the get rid of the features that do not have an interest gene ID or did not have any annotation. And equally important is you have to ensure that each of your features map to exactly, that you retain exactly one feature when many of them mapped to one entrance ID. So as you know, the way Affymetrix array is, the probe sets, you can have more than one probe set that's mapping to the same gene ID, entrance gene ID. So you don't want to report that value multiple times. So we will take you through the solution to make sure that you understood that I was only asking for you to retain one feature and drop the other features if they had multiple mappings. Then we use row t-test, some standard t-test to do the differential expression. Then finally we construct our hypergeometric instance. So that has to do with you understanding what is the universe and what's your selected entrance ID. And then finally you output the Go terms that had a cutoff value of 0.005. And your chapter 14 of your textbook pretty much covers the whole pipeline. You could have also used your Go stats package to do the homework. And I only wanted the script, and that's it. Either way, treat.txt or covtest, whichever you have used. So that was the homework. So let me show you how I did the treat.txt file. So this is my file. I have 10 files. 5 of them were lean and 5 of them were obese. I just happen to be separating them with a semicolon. Has a header, and each files are separated by a semicolon. So now let's execute the solution in R, and let's take through step by step. Okay, so let's maximize this. First thing are the libraries. I need the Affy package to read my data. I need the VSN to do my normalization. And always when you do your homework, or in future when you'll be doing your analysis, make sure what platform that your microarray has been run. So if you can find it out from the experiment details, and later on when you read the data into Affy. So if you need if your experiment has been done on 8G133A platform, and you are doing everything with 8GU95AV2, you're just getting wrong results. Then we need to get the annotations to connect to the Go database and figure out which features have Go annotation or not. We need the gene filter. Actually, we really didn't, but for the row SDS based non-specific filtering, we did not need multi-test, but actually I just use row t-test for the t-test one. And Go stats is our main package that we're trying to learn. Okay, so I set my directory, and let me move it to the right a little bit. And what are the files that I have? So I have the self files. Okay. And then I have the treat.txt file, which I'm trying to load. Okay. So now what we will do is, based from the treat.txt file, we'll construct a frame, and that frame will tell us which file belongs to which condition. And let me make sure I scroll down for the next code event. Okay. So there is our prompt. So what I do is I read the annotated data frame. I have a header in my treat.txt, and I separated them by a semicolon. So that becomes my phenodata frame. Okay, and I will get a message for incomplete line, so that's okay. I can ignore that. And it's a little hard to navigate back and forth. Maybe I can reduce it because it's too big. 24. How about I do 22? Yeah, maybe a little better. You can at least follow at the end there. Okay. So let's verify my phenodata, the frame, that it read correctly. Looks good. I have 10 files. 5 of them are lean and 5 of them are obese. So pdata pd. So now I'm going to construct my expression set object. So I need to read the files that are applicable from my directory. So the file names will be the row names. So row names will give you all the cell files. It will tell you what condition the cell file belongs, and then you will construct the expression set object and store it on your my expression set object. So that becomes your my expression set. So let's take a look at the expression set that is constructed correctly. It's reading. Okay. So now you can easily figure out, right, that this is a 8GU133A platform. As soon as you read by FE, it tells you that what kind of array it's using, how many features it's using, 22,283, 10 samples, that's within your expression set object. This is the platform 8GU133A. So you know which annotation to import, not 8GU95. So each time that you do something on your code and you construct an object, try to read it to see what exactly happened. Okay. Now what I'm going to do is I'm going to perform a VSN normalization, variance stabilized normalization on my 22,283 features in HG133A, and I will summarize that by RMA. So based on the package, if you look into your textbook example, it gives you an example of a two-color array, a VSN, but we're talking about FA metrics. So if you read the VSN Vignet, you'll see the function VSN RMA is actually written for your FA metrics array. If you have used a VSN that's done for two-color array, but you're trying to run it for FA metrics, obviously it will not work. So I use the VSN RMA function. That my expression set was the expression set object that I just created. So let's just normalize that used on VSN, and let's summarize and background correct it by RMA. So it's going to go through doing that normalization and report summarization. So one thing that I haven't investigated, but this message here is not correct because it's not a 50,000 by 10 matrix. So I have 10 sample, but I still have 22,283 features. That doesn't increase. So I need to debug to see why it's reporting 50,000 by 10 matrix. It should be 22,283 by 10 matrix. So if one of you is able to figure out why it was 56,000, email the class. So now it did the VSN. I think now it's doing the RMA, and it takes time. Okay. Now, now that your VSN and summarization is done, so let's just figure out, how many features there were. It should be 22,283. So that's how many features had 10 samples. I still do not understand why it's 506,000. Maybe It's the spots or the features, because 712 by 712 could be 56,944. Could be. Let me see. 712 times 712. Yeah, 56,944. Wow, figured it out. Okay, so that's how it reports. It reports on the features, because that's from a Affymetrix point of view, that's how many spots you have, right? So you have 712 by 712, so that means that many grids by 10 samples. But as far as your unique probes that you have used, in those 50,000 spots are 22,283 features. Okay, so that's what the 500,000 came from, the 712 by 712. So we still have 22,283 probe sets, right? So now what we need to understand is each of these 22,283 probe set either may have an entrance ID, may not have an entrance ID. What I mean that is some of the probe sets may be control FE probe sets, so they don't actually map to any gene or anything. Or in going forward, we'll also see some of these probe sets, more than one of them maps to the same entrance ID. So we have to actually pick one of them, not all of them. So we'll take you through that. So the annotation that I need to use to get to my entrance ID would be HGU133A, right? Because in your example, you may have had HGU95AV2, but you know that's your platform, so that should be your environment. So then when you call this function feature names dvsn, right, it gives you all the probe sets. So if you just do that, it gives you all the probe sets. So you know these are anything that starts with the AFFX prefix, so that's a control probe set. It will not have any entrance ID. And so first what you do, the way this function is written, for each of those probe sets that you have, call the environment, which is this annotation HGU133A to entrance ID, and mget function will get you all the entrance IDs. So very simple, you know how you use the annotation. And it was exactly on your book or on your Vignet for the GoStat package. So let's get all the entrance IDs. So let's take a look at it, you know how it looks. So what it does, I'm just looking at the first top 10. So it gives you the probe sets and tells you what's the gene ID, entrance ID for it. So for probe set 117_AT, the entrance ID is 3310. So that's what the function did. It went through each of your features, called the annotation for the correct environment, gave you the entrance ID. If you look at the bottom, very interesting. See, anywhere that is AFFX that started with your control Affymetrix probe sets, NA means not available. There is no entrance ID for them. So what you have to do now is out of your 22,283 probe sets that you have to write a function which will, anytime that you have NA, it will indicate it's false, I don't want it. And anytime it did not have an NA but had an actual number, those are the probe sets that you want to get, right? So when you apply so these are all of your feature names. So you have 22,283 of them. I showed you the first few ones. So these you will retain these because all of these probe sets have an ID to it. But if you look at the bottom of it, just so you can visualize, this has NAs. So that means you want to get rid of this. You don't want these probe sets. So what I do, and I don't know whether I copied it from book or I wrote it or it's in the Vignet, I'm not sure, but that's the function. You can use is.na, right? So what is.na does is whenever something is not available, right? So not is.na means x is not null. So if you supply x into this not is.na, this will return you to say either, so let's say x is 7, right? So if x is 7, it's not null, so not is.xa will return me true, that it's not null. But if x happens to be null or na, then it will return true. So that's what it indicates. So then what you need to do, remember in R, you don't have, so when I'm going through all my features, so I have about 22,283 of them, I don't need to write a for loop to do that. So R is very good where you can write an sapply type of function, apply family type of function. So what it does, it will go through each of this entrance ID and it will check for this condition to say, is it returning me something saying it has a NA? So if it's NA, so if it's not NA, then it will be true, and if it's NA, then it will be false, because you put the not. So this sign over here means not. So is NA itself, when something is NA, it returns true, and when something is not NA, returns false. So not NA works in a reverse Boolean. I think you guys follow it. I don't have to kind of ponder with this too much. So if you do this sapply function, so it actually, that's what it's doing, right? So if you do that, you see when I showed you the tail, these bottom fx was NA was actually true. So not true is false. So it's going to give you all this as false. That means end of the day you actually don't want it. And the ones that had an entrance ID where it was not NA but actual something else, if it's not NA, it will actually have a value. So for those, when you apply the sapply, will be true, right? So it's pretty neat. You can do a lot in R with just one line, where in any other language you have to write a loop and construct a lot of things. But I hope you're appreciating more and more, how you can do many things as long as you know in which context you're using the apply and what your function is actually doing. So your sapply entrance ID not A is giving you true and false for each of those probe sets, whether you either had an entrance ID or didn't have an entrance ID. So if it's true, or if you construct a bigger matrix, so from your list of 22,000, your subset, whenever it's returning true, it will return the subset. When it's false, it's not going to return the subset. So you have entrance ID, you can accomplish by writing this particular line here. Okay. So that's, I wanted to spend some time, what is.na means, how you write the function, so you can visualize the true and false. So every entrance ID that had a true got selected, and then those are the entrance ID itself that you're selecting, and then you're storing it into the have entrance ID. So if you look into the number of features that have entrance ID, you started with 22,283. So if you look at the length now of it, so it looks like 22,338 has entrance ID and the balance don't. So 1945 don't. And you can I just did it, you can check it. So you can take the length that you started with. So you started with DVSN with 2283. So if you subtract 338, so that gives you 1945 that you are actually going to disregard, which is mostly these control ones, AFX, that anything that starts with AFX that you are not interested with. Just some math. So I just did that so you make sure numbers add up, so you're following what you started with and what you're removing step by step. I think you could have also used the NS filter function from the book. You don't have to go through all these steps, and it will give you a log file. But I followed the vignette, so each step was broken out, so I can follow by each line of code what exactly happened, then to just rely on a big function, which I don't know how it was constructed unless I study it. But then you can verify that from a log file. But this is a better way to break it out in smaller chunks and do each of these code one by one. So because some of those of you who want to do programming based bioconductor and others, you want to know at each unit you want to question what's happening. The other option is just to have some blind faith on some function and it returns you some value. But it's just a matter of philosophy what you apply, at what level you want to break out and how much control you want to have. And as you start maturing, you'll just write your own functions and your own classes and objects. Okay, so we are down to 2338 now. Okay, so what we do, I started with my DVSN, right? So have entrance ID is 2338. So I want to go down from my 22,283 to 2338, and I do that by subsetting my original array. So my reduced one, I store it in this expression set object, right? So if you actually select it, you can actually verify. Now you're down to 2338 features for 10 samples. So you got rid of 1945. Okay. Now, now that I am down to only those probe sets which has entrance ID, I also are only interested on those entrance ID that has a Go annotation. So it doesn't mean that we know everything about all the 20,338 features and someone has documented or found Go term for those entrance ID. Maybe there are some genes that we don't have Go yet. So if you don't have Go, and at the end of the day you're trying to construct a hypergeometric test on your selected Go terms, so the entrance IDs that are not returning you any Go term are not going to be anything valuable for you. So you have to not consider those features on your universe. So your universe should contain only those features that have an entrance ID and those entrance ID that has a Go. Okay. So just like the way we figured out what were our different entrance ID for each features, I can still, same way, instead of calling HGU133A entrance ID, I can use HGU133A Go, right? So that will tell me for each of my entrance ID what are the different Go annotations that's available. So mget feature names. So that tells you, this retrieves only those entrance IDs that has Go annotation. So I write a bigger function, again sapply, and it's a little big. So in the sapply, I first get on this part everything that has a Go annotation, and then I do the same thing. So for each of those entrance ID where it did not find the Go annotation, it's going to mark it as NA. So just a little different function than we first showed you here. Function x not is dot na. So we just say if it doesn't have, if it happens to be just a length of 1 and it happens to be coming with the na, that means I'm not interested in those entrance ID because those entrance ID doesn't have any Go annotation. Otherwise, if it's not na, that means it give you an ID. I want to pick up those entrance IDs or retain. Just the same concept. How you went from your original features to only those that has entrance ID. Now you're going from your subset to those that has Go. And you do that by sapply. Okay. So now it goes through each of your 20,338 features with entrance ID and figuring it out which one doesn't have a Go as NA and which one has a Go. The ones that have a NA, it's going to return as a positive, as false, so you're not going to retain it. The others you will. Okay. So you have your, so these are the ones that have Go. Okay. So you can see by selecting it, each of these features has a Go, so it's true. Probe sets has a Go, so it's true. Anywhere that and this feature doesn't have a Go, so that's false. So that's your what you return out of your sapply. Sorry. So it marks it as true or false for each of them. So if you want to now know how many of them doesn't have Go, not. So if you, this is very interesting how you do that. So when you do a not, so it only gives you the false. It doesn't give you the true. So then if you do a sum over all of that, it gives you a count. So then what happens is 1098 of those rows, and you count it. Anytime you get a false, so that count as a not. So you counted out all of your false against your 2338, happens to be 1945 of them had false or no Go annotation. Okay. So you are interested with those entrance IDs that has Go. So then you will only get those with have Go, and then you will subset that. So if you subset that and you see it now, so that's 1900, 240. So then again, do the math. So the math would be You started with 2338 that did have entrance ID, but either had Go or did not have Go. You know 1098 of them definitely did not have Go. So when you subsetted it, you should have ended up with 1900 420 probe sets with entrance ID with Go. So you get it there. Again, all this could have been done in one line following your test book, but I liked following the vignette where I know exactly at each line what am I writing, what it's returning, and how is my data set going from 10 to 8 to 7 to 5, whatever. So you follow the progression. So all those filtering are done up to this point. Now we're going to do what we have done a lot in our earlier homeworks, which is non-specific filtering. So in the past, for the non-specific filtering, we have only retained those features which had an IQR greater than 0.5 or greater than 0.8. Because anything in the with a low IQR value means they're very close to each other, and gene features that have very close value to each other among samples, we're not interested, because they're not going to give you any differential expression anyway. So I think in the past I have also shown you, other than IQR, how you can actually also use SDS, which is the standard deviation for each of those genes between the two samples. So between two samples, if you have a low standard deviation, that means they're most likely they're not a candidate for differential expression, and if they have a very high standard deviation, they are definitely a candidate for differential expression. So by doing the row SDS and calculating the standard deviation for each features at each of your each features, then for each of your arrays, we will try to see what is this low SDS and what does high SDS mean, and what is my cutoff. So you actually have to call it, plot it, and see what's happening with your data. So let's just calculate row SDS, right? Standard deviation for each of your features that you retain, which will be out of your 19240, and calculate the standard deviations. And you can do that by the row SDS function. Okay, so I think we're here. And shorted SDS means that you break up your data into half. So it actually shows you, if you break up your data, your number of features into half, what's the middle value or median of your standard deviations. And we can usually visualize it by the picture. So you call the short function in R that gives you SH value, which is at the middle, and we will see that briefly in the picture. So if you break up your data, the 50% point, the row median is 0.13. So there will be some data left of it, and there will be data some right of it. So as you know, the data that's on the left of it, you're not interested. Data that's in the right of this, you're interested. And let's visualize this, right? So let's visualize. So let's draw a histogram and of our row SDSs, and see how it looks. So all the SDS that we have calculated are stored in this variable. So let's draw a histogram. Again, this is in your book. So that's your histogram. Okay, so your SH value, and there is a way actually also to print and line up the SH. Your SH value was 0.13. So somewhere over here, if you draw that, the 50%, so frequency. So you have, so this bar means you have 2,000 features with the row SDS of I don't know, 0.18 or something. This is 0.1, maybe halfway, and you have about 1,500 of them. So 0.13 comes somewhere around here. So left of it, all these features that you have are only going to have row SDS less than 0.13. So you don't want that. With the low SDS means you have low standard deviation, so you're not interested. You're interested on these, which are showing higher and higher standard deviation. Okay. So I am only interested in retaining where my SDS is greater than SH. So SH is 0.13. 0.13 will fall somewhere here. So I'm interested on the greater line to the right. So that's what I do here. SDS is greater than SH. And if I do that, what happens? I started, remember, I started with 19,240. So now that I are only retaining what's on the right of my SH. Oops, I think I did not draw the line correctly. Let me redo it. Okay. So my SH is 0.13. Did I not copy this line correctly? Control R. Okay, so that. So a B line is going to actually draw the shortest point. V equals to SH. Okay. Now it did it. I think I didn't copy and paste correctly. So that helps you visualize. So get rid of everything that's on the left. Only retain where your row SDS is greater than SH. So SH is right here at 0.13. So I do that. So now I should be down to 12,612 features. And I started with 14,000 something. Okay, so my non-specific filtering is done there. 12,765. 12,612 actually. Okay. Okay. So now what I need to do, where am I going with this? Okay, so let's just figure, if I just do the row SDS, what does it tell me? It gives me, for all my 12,000 features that I have, it tells you the exact row SDS value, 0.2. For this feature, this is your SDS value. For this feature, that's your SDS value. So that's what that's giving you. And what I additionally did is, instead of relying just on 0.13, if you look at my picture here, I set off a criteria. And you don't have to do that, but I am looking at this picture and set up a criteria to say, like we do IQR, whether it's 0.5, whether it's greater than 0.8. There is no law that tells you that you always have to use greater than 0.5 or greater than 0.8. It's up to you, where and how you're setting off your cutoff value. So when I'm looking at it, even though my row SDS gives me 0.13, 0.2 to me is still low standard deviation. So if I establish my criteria as 0.2, that's still a low enough standard deviation. So I'm additionally saying, I know that row SDS is 50th% is giving me at 0.13, but 0.2 to me is a criteria where I can ignore and everything left of it. So I did an additional filtering to say, get rid of everything that's left of 0.2 and give me anything that's greater than 0.2. I don't expect you to do that in homework, but that was my way of doing this analysis. So I set off a cutoff value for SDS as 0.2. That was my, and I think I asked you in the homework, you pick your cutoff. So we will review that accordingly. So I set up a cutoff of 0.2, and then I'm only retaining those that are greater than my cutoff of 0.2. So if I do that, so then finally, I think I end up with 7,612 features, or 7,467 features. I don't have the numbers correctly noted here, but same thing. So, so where am I? I started with entrance ID, only retained those, then I only retained those entrance ID that has a go. Then I did some non-specific filtering with row SDS, and I only retained those that are greater than 0.2 of row SDS. Now the big challenge comes. I don't know whether most of you got this in homework or didn't. I haven't had a chance to look at your homework. But what I wanted specifically in the homework, and if you see this line, ensure that probe sets map to exactly one entrance gene ID. So what I mean by that, or meant by that you could have multiple probe sets if they're all mapping to one entrance ID. I only want one entrance, feature to be retained. So, for example, you can have probe 1, probe 2. They both map to gene 1, gene 1 and gene 1. So this one has a value maybe of intensity of 10. Maybe this one has an intensity of 12 or 23, whatever. But I want probe 1 to retain, only one probe to retain out of these two. So what should be my criteria? If I only want one out of these two, am I going to go with the one that has a higher intensity? But sometimes higher intensity doesn't mean much. So what criteria I establish is, let's look at the SDS. So if I know the standard deviation between two samples, between lean and obese, if my SDS for probe 1 for the same gene happens to be 0.2, and this one has an SDS of 0.35, so I will pick this one because this has a potential of showing me a higher differential expression than this one would. And I think in the Vignet they do it by IQR and others, but that's what I'm getting to, and that's why I needed to know the SDS of every single probe set. And then when I know that both of those probes map to the same gene, then get rid of this because the SDS here is lower than the SDS that I'm expecting to be retained. So that's how I ensure by retaining only one probe with the highest SDS value. And that's what I continue doing in our code. So I find the largest. So I think this was already figured out on your Vignet, but they probably did it with IQR. But here I show it by SDS, not IQR. So that was the platform. You already have all the SDSs figured out here, right? For each of those probe sets, you have the SDS. So the function that we already are leveraging is give me the one that has the highest SDS. Find largest. Okay, so that's the code there. So how many it retains is 5,750 features. Is retained that way with the highest SDS, and dropping those that has a lower SDS but mapping to the same entrance ID. Okay. So then let's just subset it. So now, oops, sorry. So if I do that, so my length and NS filtered. What did I do wrong now? Okay, so did I do this? NS filtered SDS. Okay. Okay, so if I select that, that gives me the SDS for each of them. So unique genes. Okay. That and okay. Alright, I didn't follow the error. Either I did not select, I think I did not select that. I think I just did up to this part. So that didn't work out. Okay, so now I have my NS filter. So here I have 5,646 features. So now I have ensured that each of those features have exactly one single entrance ID mapped to it. They all have Go annotation. So that becomes my universe right now. So all this work that I did, starting with only retaining entrance ID, only retaining one with Go, only retaining where SDS is greater than 0.2, and making sure that not multiple probe sets are mapping to the same gene. So I'm down to 5,646 features of my 22,000 that I first started with, and that's going to be my universe of possible entrance ID genes and Go annotation that you can have. And out of those 5,466, when you do a t-test, you can pick like maybe 100, 500, or 700, however many that has a t-test based cutoff value. And then now you're going to finally construct your hypergeometric parameter to say, okay, I had a universe where maximum possibility was 6,000 entrance unique ID that's there. But now you picked out of that, urn or whatever, 700. So what's the likelihood that those 700 or 500, however many features that you have picked with the Go annotation, wouldn't have been picked just by chance? Right? And that's what the theory we went behind Ball and Earl and hypergeometric distribution. So that will be the final phase of our homework. So we do a t-test, simple t-test on our data set. Okay. So before we go there, so now that I have my 5,550, so let's define the universe. So my FE universe I'm assigning as only those features that was in my NS filter, the 5,750. So if I get the feature names, I stored that as in my FE universe, and which should be the same as my entrance universe, because by this time I make sure all my FE matrix ID or probe set ID has an entrance ID. But let's just store them as FE entrance ID into my entrance universe. So this will have the FE IDs and this will have the entrance ID. And they both should be the same and 5,700 something, so that both of them has FE and entrance. So that's my universe. So that's maximum. And remember that I showed you a graph with p-value and at any universe. If you make your universe very large, let's say if you made your universe 22,000 all possible features, then when you picked your t-test based p-values, so if you have a very large universe, your p-value is going to be actually smaller. But if you have a higher. But if you have a smaller universe, you have a higher likelihood of getting a smaller p-value. So think about the relation between what's the impact to your p-value when you pick a very larger data set of universe versus a smaller data set of universe. So my FE universe and my entrance universe has been defined, and there should not be any duplicate. You shouldn't have got an entrance ID that's coming twice, and I didn't. So that was just an error check I did. Now I start with a simple t-test, and my criteria for t-test here is 0.05. So I set a criteria. My NS filtered means so I'm down to an expression set of 5,646 features. Okay, I have 10 samples, and my samples phenodata looks like, just to verify, I have 10 samples, so 5 of them lean, 5 of them obese. I'm down to 5,646 features based on my entrance ID and annotation and row SDAs, and no duplication of entrance ID. So now on this reduce, which is my universe, reduced data set, out of this universe, I want to filter only those features that has a p-value of less than 0.05 or equal to 0.05 when I do a simple row t-test. So before I do the row t-test, let's just figure out what are the unique conditions I have, which is lean and obese. Right? So in the row t-test parameter, there are two things you have to give for the row t-test to calculate, and this is also on your book. For the row t-test to calculate, you have to give them what's the expression set object that you want to be filtering. So I have right now 5,600 some features, and that's all I want to do the row t-test on. I don't want to do the row t-test on 22,000 features, which I started with. So big difference in how we're approaching this. Then what are the unique conditions of your samples? In my case, it's lean or obese. So I have to do a factor on my pheno data type. So if you do a factor, what is a factor? Factor just gives you distinct. So you're distinct. So each of these, 5 of them is L and 5 of them is O. So levels gives you within the factor the distinct. So you have either lean or either obese. So those are the two parameters that needs to get into your row t-test, because if your parameter is not correct here, if you did not factorize it like that, and if you did not supply a correct or expression set object, your row t-test will not calculate. You'll get an error. So that's that. So let's calculate the row t-test on each of them, which it does. And now let's look at them. So you did some row t-test and you assign it to t-test. So what does it look like? So it looks like it lists out each of your probe sets, calculates the test statistics, okay, and then calculates the p-value. So what you want to do now is you want to dollar a reference to this p-value column, and you only want to retain those probe sets that are less than or equal to 0.05. So just based on this top 10 or head data that I'm showing you, you should ignore this row. This row should be retained. Ignore. This row should be, well, actually it will just barely miss it because 0.053. This should be also ignored, 0.2. So the way you can actually refer just to the p-value is if you do t-test $p.value, so that you only get the p-values. You're not doing anything with the statistics over here. Okay, we're almost there. Okay, so dupes, I figure out, I give the 5,000, I do the row test, I look at that. So I've prefix, right, $p-value, so that gives me all the p-value. My t-test cutoff initially, I've already said less than 0.05, so it has to be less than 0.05. Then I store all of those in my selected p-value, which I say SMPV. So then from my filter data set of 5,000, I only get those that meets my condition of SMPV. So I won't go from there to this subset of filtering. So do that. Now I get the subset based on whatever met my cutoff criteria. So maybe 700 or something, I don't know, will meet my criteria here. 702 features out of 10 samples met the criteria, or p-value was less than 0.05. Okay. Now, I am pretty sure that all of these will also have entrance ID. So what I want to do now, because when you're constructing your hypergeometric test, you have to see what are the different parameters that is asking. It will ask what are the entrance ID that you have selected, what was your universe, what annotation you're using, what ontology you care for. I only said in the homework biological process, so it will be BP, and what is the cutoff value based on which your hypergeometric test should calculate. And there is also under and over how many direction you want to test. And finally, yes. So then I already stored the entrance universe in my the earlier, which is 5,000 something. So whatever 700 that I have selected, I actually have to convert it so it actually gets mapped to an entrance ID. You have to map. So this is actually it's expecting gene IDs. You cannot give them feature names. And then the universe gene IDs has to be we already figured out, what are the different entrance ID that was in my universe for 5,000. So then over here, whatever I'm selecting, using this annotation for those features, let's figure out what were my entrance IDs. So this should be 702, right? So these are all the entrance IDs that you have, and there should not be any duplicate. Okay, so that's when you come to think of it, it may seem a little complicated, or maybe it's very simple, but end of the day, you're trying to drive in constructing this parameter. And what is that you need? This you need selector that came from t-test. That was your original one that came from having an entrance ID, having a go annotation, and meeting a non-specific filter criteria. So that was your universe. So you have to understand very clearly what was your universe, what you just selected based on your t-test, and what's your cutoff value, and based on that you can actually calculate your hypergeometric test. So I think in the homework I asked 0.005 maybe. for your hypergeometric. Yeah, 0.005. So let's see if you even get anything. That's a very strong cutoff criteria. I don't think you will, but let's see. So I selected 702 and my universe was 5,000 something. So I will only pick, so I'm doing a hypergeometric test to say, okay, I picked some things out of the basket. What's the criteria that I picked it by chance or it's really significant? So then so for each of those ball that I was, or the genes or go annotation that I was picking from the basket, through hypergeometric, I'm calculating a probability or p-value. So the p-value is less than 0.005. That means the go annotation that you picked did not happen by chance. It's significant. So you will retain those go IDs. Those go annotation that has a very high p-value, that means you could have just might as well picked it. If I didn't tell you anything, by chance you could have also just picked those go annotations. You didn't have to run all this experiment. So those go annotations which has a very high p-value, you will not consider as significant. Those go annotations that has a low p-value, you'll consider as significant. So in the homework I say 0.005. So let's do that. So that's the core or heart of your code, where you are defining universe, defining annotation, defining, it has to be biological process. You could have also done molecular function. You could have also done, instead of all these go annotation, you could have also done a KEGG pathway, which is also in your exercise in the book, but fair enough just to do it for one. So it does that, constructs the parameter. So did you even find anything? So you supply it to the hyper-G with your parameter that you just calculated and see what does it list. So it's we'll see what's the outcome. I think I didn't get anything for 0.005. So I lowered my criteria even more to 0.01. This is a very, very low cutoff that I gave you. But so additionally, I upped the cutoff criteria, so then it should give me some go IDs that are not happen by chance, that has a significance of being selected based on my p-value. Okay, so it's not done yet. It takes, again, this functions are time processing, and we should be able to wrap it up in a few more minutes, then we can move into linear modeling. I don't know why it was different. I don't know. It should be constant. Your data values, it's not changing. So I don't have answer to that. Why it changes, if it does. I'm not doing HG over. I did this HG over, right? I copied too many times, HG over, HG over, HG over. So I just have to select once. So basically it will either tell you that it did not find any go annotation based on the criteria that you're setting. Then I actually up the criteria to 0.01. Then I get like 10 or 20 go annotations. Then I save it into an HTML file. Then I tell you what those go annotations are. In addition, if you look at your chapter 14 in the book, what they do, they actually have a graphics package that they import, and they can actually draw the graph of the cyclic graph in a go annotation to say, which go is related to what. But that package of the RV graphics is actually not working for me. I think it's telling me I have to uninstall and reinstall R. But I will show you the code following the textbook. If any of you had success, you can do that. So at 0.005, actually you have 5 of them that do get selected. So if you did your homework based on 0.005, you should be reporting to me 5 of them. Because when I did it with 0.001, it didn't give me anything. So 5 should have less than 0.005. 0.001 is a very small hard criteria, and that did not return anything. So final thing was draw the histogram of HG over, and you can display everything that's less than 0.005, and then you can save it into an HTML file. So that will be 0.005. So I can draw it and do the reporting. And I don't have to show you the histogram. Let me just show you these are the 5 Go annotations, right, with the p-value less than 0.005. And then there is a way, so these are the 5s that I would expect that came from your homework solution on 0.005. What additionally that it did not work for me is this graphic RP graph Z. So when I'm trying to load it, I'm getting an error where the library DLL is not found. So I need to see why I'm not able to load the DLL, or maybe I need to uninstall or reinstall my application, but I did not go through that. But it's pretty neat if one of you are able to do this. So basically what it does, it gives you for each of those 5 Go annotations that you have, what's the connection or the graph between them. So that didn't work. But that was not part of the homework, but I wasn't expecting you to do that. But just something I just thought interesting. If any of you played around with this, let me know. Or else that was pretty much what I was expecting, and the HTML report will be done just like the way your book is. So we'll compare and see if these are the 5 that you did or did not get. And then when I did it with 0.01, I actually got about 20 of them. So it all depends, where you're setting off your criteria. So let's conclude with our homework 6 review right now, 5 review. I will upload the solution and I'll review hopefully next week, along with when you're submitting your homework 6 for the gene set enrichment analysis. Okay, and let's talk about linear modeling. There's a lot of theory behind it. So let's just briefly review what I'm expecting you to learn and upload next week. So first of all, you have to upload this. I will put it in lecture 11 folder, the LIMMA user guide PDF. So read the user guide. It's like 300-page user guide. So read it like I did. I will go through this PowerPoint presentation today. So we have to understand before we start doing LIMMA what's a design matrix and what's a contrast matrix. This is a good lab. Feel free to go through it. I'm not going to cover it. So it gives you a good overview of materials that we have covered up to date, this date. In addition, it does show LIMMA. Next week, Sunday, when we meet, we're going to do this lab, time series lab with LIMMA. So that will help you, and the way I designed the experiment, homework 7 follows this time series lab that we'll do next Sunday. So again, why are we using LIMMA? So to this date, all the experiment or all the data set that you have worked with had a single time point, and you are uploading these 10 or 20 cell files. They either belong to condition A or condition B, and you're comparing between them and figuring it out, what's the top expressed gene, and mapping them to pathway, mapping them to Go annotation, etc. Going forward with time series, what you need to understand that in many times you can do an experiment, let's say cell cycle or other development or phase, etc., where you have a data set for 1 hour, you have a data set for 10 hours, and you have a data set at 24 hours. So you may be interested with the question to say, what were the genes that was always upregulated between all 3 time points? There could be condition where you want to compare between 10 hours or 24 hours. You want to say what's upregulated between 10 and 24 but did not have any upregulation on 1 hour. Or you can ask the question, show me those genes that were actually up from 1 to 10 hour and then actually went down from 10 hour to 24 hour. because at different time phase or different cycle, your genes can either go up or go down. They can stay down constantly or they can stay up constantly. So to do this kind of comparisons, you have to use the LIMMA technique, and it's not on your textbook. I don't know why they didn't cover it. So I think maybe it's a good feedback we want to give to the authors of the bioconductor case studies to add a chapter on LIMMA. And also to wrap it up, I think what you guys are working on your project, which is meta-analysis, that's also a good topic. So that's pretty much what's left of us learning, of dealing with multiple time points. You guys are working with combining multiple experiment, which is the meta-analysis. And then another topic I think is also interesting from me working in a pharma is connectivity mat and drug signature, which is similar to JESA. So you can actually mine different compounds and try to see what are the different patterns those drugs leave on your experiment. And then can you learn something and find some indication of drugs that you may be using to treat condition A, but at the same time either it's giving you a side effect or has potential to cure another disease. So that's another topic I also find interesting, and maybe for the remainder of the weeks we can touch base on drug and compound mining and drug signature through connectivity map. So let's try to understand LIMMA for today. And so what I did here is I drew up a few things on my Excel spreadsheet. And what I really want to convey today is at least you should end today's class by understanding what's design matrix and what's contrast matrix. Because once we get those two concepts out of the way, the next Sunday when we meet to do the lab for the LIMMA, the time series data, we don't have to think about the concepts, then we just strictly focus on the code. So there's some notation that you need to understand. So I try my best to explain it into an Excel file. So what I'm trying to explain here is a 2-color array, okay, not Affymetrix array. So you did your first array, and remember for 2-color, you need actually one array to test 2 conditions. For Affymetric, each sample will have their own array. That's Affymetrix, 1 array to 1 sample. But for 2-color, you can use 2 sample in 1 array. You can dye one of the sample as red, and you can dye another sample as green, and you can put it into the same array. So you need half number of array in 2-color than you would need in Affymetrix. So think of an experiment that was done on a dual color array. So you had a reference sample, let's say that was labeled with red, and you had a sample either treated with drug, or it could also be placebo, normal, whatever may it be. Let's call that sample A. So the notation that you have to follow is A with an arrow that's going into ref. So A was done with a green dye, and ref was done with a red dye. And A towards going to ref, right? So that's just a notation. It doesn't mean anything more than that. So at this point, it's representing A is a sample, ref is a sample. The point where the arrow is going tells you that's labeled with red dye, and the reverse of it is labeled with the green dye. So now you may be interested to compare this reference sample with the sample A. You want to see what's the difference between your reference sample and then the new sample with let's say treated with drug, right? So when you do that, you say ref minus A. So that's the comparison, ref minus A. So if you want to say this experiment, this is how it was designed, and you are saying it as ref minus A, so let's assign a value of 1 to that. Okay? So then inversely you can say A minus ref, which is negative of that, should be minus 1. So by attaching this ones or minus 1, you're actually telling the package who's labeled with what dye and what's the direction of your design. You have to first establish how is your experiment designed, and this is the notation you follow. So ref minus A, so the arrow is going towards the ref, so it's positive in that direction. But if you want to say A minus ref, so that will be minus 1. So that's your first experiment. Second experiment you did differently. In this array, you actually had the reference sample, so you did a dye swap between these two experiments, right? So in this die swap, your reference was actually green and your A was actually red, just the reverse. So arrow is going towards A. So if you want to compare the difference between A minus ref, so that's 1. So same thing. Or for this experiment, inversely, ref minus A will be minus 1, right? You just take the opposite. Which is nothing but notation. There is nothing fancy going on here. Okay? Ref minus A is 1, so A minus ref is minus 1. Here, A minus ref is 1, so ref minus 1 is minus 1. Okay. Finally, you had the third experiment where your green die was ref and your red die was B. So you had actually in this 3 experiment, you have 3 samples. One sample was reference, one sample was, let's say, drug A, another sample was drug B, and you had your reference control sample. So in the third experiment that you did, where the arrow is going towards B, right? So B minus ref will be 1 and ref minus B will be minus 1. So those are some of the notation. Before I go to the slide, I want you to understand what's A minus ref, ref minus A, or ref minus B, the comparing between two, when it's 1, when it's minus 1. Hope I made some sense. So this is the design on a notation, and probably in the slides you will be better able to picture them. So you had 3 arrows representing 3 experiments. This arrow represents A ref minus A. This arrow over here represents A minus ref, and this arrow represents here B minus ref. So whichever direction the arrow is going, so that's your sample that you want to compare. B minus ref, right? This is A minus ref, and this is the arrow is going towards ref, so this is ref minus A. So all these scenarios, it will be 1. Okay. Now, if you want to compare B with A, there was no example or no array done directly comparing B with A. So you can compare A with ref very easily, right? So this in this experiment, which I have highlighted, if you go A minus ref, then you can see what's the difference between A and ref. You can do the reverse between A and ref too, ref minus A. But there was no experiment you did directly between A to B. So to compare A with B, you have to go from A to ref and ref to B. So we just do some very simple algebra. So if you're comparing B minus A, it's the same thing as writing B minus ref minus A minus ref. So minus ref, and this becomes what? B minus ref minus A plus ref, right? Simple algebra. So minus ref plus ref cancels each other. So in order to compare B minus A, you have to go from B minus ref to A minus ref. That's how you compare between B minus A. You use these 2 arrays. So that's how the B minus A notation comes in. So then, what you finally need to do, I always say the word finally is never final anywhere. So then you have to understand what's the design matrix. So design matrix, what you do is you line up all your experiments, then you line up your sample. So A minus ref and B minus ref. So if you look at the experiment 1 that we talked about, it's an association only between ref and A. There's nothing to do with B. So if you have a matrix where on the rows you're talking about the arrays, and on the columns you're talking about the sample, and what you are talking about is now comparing A with ref, right? So in experiment 1, A minus ref will be actually having a value of minus 1 because the arrow is going to the direction of ref. So red die is actually used under ref. So ref minus A has a positive design. Positive tells you when you use ref minus A with a value of 1, then you can tell that red die was used here and green die was used here. But if you want to do A minus ref, then you have to swap it and it will become a negative value. So if I am comparing A minus ref, for my first experiment the value will be minus 1. For the second experiment, A minus ref, which is actually 1, right, is positive. And in the third experiment, it has nothing to do with A and ref, it's between only B and ref, so that will be 0. Right? So if you look at the design matrix here, so A minus ref for the first experiment is minus 1, second experiment 1, third experiment is 0. And if you're doing B minus ref, very simple. If you look at your first two experiments, there is no reference to B, so in both scenarios it would be 0. And on the third scenario it would be 1. B minus ref is 1. So that's your design matrix. Minus 1, 1, 0, 0, 0, 1. So that's design matrix. So now let's move on to the slides where we will also talk about the contrast matrix. Contrast matrix is when you actually what are the different comparisons and how many different comparisons you're interested. So in my example, if I have 1 hour, 12 hour, and 24 hours, that's in your homework, right? So if I tell you compare 1 hour with 10 hour and 24 hours, where everything is up, so that's one comparison. If I tell you compare only between 10 hours and 24 hours, that's your second comparison. So that's what will build you. Your contrast matrix is how many comparison that you're looking for or someone is asking you to do. So that's contrast matrix. And your design matrix is how you tell LIMMA that how is your experiment set up. So there is one way you have to, so this example that I show you is how you would do that for a 2-color array. And then FA matrix array is actually much more simpler, the design matrix, and we will go through the slides and to show you, how you would do the design matrix for FA matrix array. So as long as you're comfortable with design matrix and FA matrix and contrast matrix, you can very easily run the LIMMA package. In addition, so this time series lab that we're talking about, where I think it does it with Drosophila embryogenicis time series data. Yeah, so this is the lab we will do next Sunday. And also in the lecture, there are a couple of, I also tell you to read this paper for the overview of the theory behind LIMMA and empirical base. So this is, and then on this particular, what I just talked to you right now on the notation. So if you want to understand what I talked about the notation and this experimental design, start reading from page 2. So it talks. So I just showed you actually this design here in my Excel spreadsheet C, where you had reference 3 samples, A, B, and reference. So this is reverse die swap between A and ref, and between ref and B was the third one. So I just went through that one. So over here is just one comparison, A with B, 2 samples. Over here still 2 samples, but do a reverse die swap. This is a diagram for 3 samples. Okay, and no die swapping going on, just 3 samples. So based on how you have designed your 2-color array, there will be a notation and a diagram for it. And once you have that diagram, you can actually get to your design matrix from the diagram. And your contrast matrix depends on how many ways you want to compare. FA matrix always ends up with a very simple design matrix because it's one array to one sample. So the parameter and the number of sample is same, which we will cover. So you don't have to worry too much about FA matrix array. It's the simplest way to design the design matrix. But 2-color array, when you're dealing with it, gets into very, very complex. But let's just go through the slides and then we can end for today. So I will also upload this slide along with the lecture material. And okay. So I don't know. So let's see. Maybe we can do some Google with the graph package. I don't know why it's not working. I'll try with my Mac also. But it's interesting, Suzanne, that you also got the same error for the graphics package. Okay. So this is a very good slide by Natalie Thorne. Very well put, extremely well done. Slides will speak better than I can speak to it. So just go through that. So this is our linear models to understand from experimental design to model. So what she starts out with by just the example I talked about. So you have 3 samples here. First 1, 2, and 3. So each of this array represents a sample. So over here your reference was done with the green dye and your sample A was done with the red dye, and this is a die swap of the same. Swap the dies, right? Now reference is green and this is red, and over here reference is red and B is green, and over here reference is green and this is red and reference is red and A is green. So just a die swap going on. So then when you talk about a comparing between your A with your reference, right? So what's happening is you will have some baseline value, which is your control sample, and when you treat the other sample with the drug A, it will have some changes. So that's the difference. You start with the reference sample, which is your baseline sample, and that has some baseline gene expression values. When you talk about another sample, which is, let's say, treated by drug A or drug B, so it will be either some of the genes have the same value as baseline, plus it will be something, either when it's the same value, so the A will be 0, but if it's different, then A will have some other value. So A is a little different than baseline by A, B is a little different than baseline by B, and reference was the baseline. So when you're comparing A with ref, right? So A is baseline plus A, and reference was baseline. So A minus ref, we're establishing a value called A. Comparing B with reference becomes B, and comparing A with B, you have to go through 3 of them, so which is A minus B. So then it talks about what are the sample types, talks about what are the parameters, so go through this slide. And it also talks about a parameter independent of parameters. So this is a good topic to understand. When you look at these two samples, right, A and ref, you're comparing sample A with your sample ref, and you're comparing also your sample B with your sample ref. So these two do not depend on each other, right? When you want to compare A with ref, it has nothing to do with what's going on with B. And when you're comparing B with ref, it has nothing to do with what's going on in your experiment 1. So your experiment 1 and your experiment 3, or experiment 2 and your experiment 3, they're completely independent of each other. But if you want to compare A with B, that's not independent, because to go to A with B, you also have to understand this array, and you also have to understand this third array. So the way it works is in your two-color array, your number of parameters that are independent will always be the number of sample minus 1. So if you have 3 samples here, your number of independent parameters will be 2. There are 2 independent, but this, when you're comparing A with B, that's not independent, because you have to go through 2 arrays to get to A minus B. So that's what it's talking about. But for your F matrix array, each sample has its own array, so number of arrays is equal to number of parameters. And remember, for your two-color array, its number of parameters is equal to number of sample minus 1. So over here will be 2. Okay. So this is a better picture, and I think I wanted to draw it out on the Excel also. So you had 3 dual color arrays, so 3 experiments, so that goes row wise, so you're actually constructing your matrix. And the parameters will be, you have 3 arrays, right? So you have 2 parameters, and you're only interested about the independent parameters. So A minus ref is an independent parameter. It doesn't care what's happening with B. B minus ref is an independent parameter. It doesn't care what's happening with A. A minus B is not an independent parameter, again, because to do that you have to go through 2 of them. So when you construct your design matrix, on the columns you talk about the independent parameters. On the rows you have your experiment, so that's your matrix, and it's very nice how she carries it through here. So if you are only talking about slide 1, A minus ref is 1, okay, and it has nothing going on with B minus ref, so that's 0. So from the slide 1, experiment 1 perspective, yes, it tells me what's going on with A minus ref, and it's going to the direction of A, so A minus ref is 1. Whichever direction the arrow is going, that's positive. So A minus ref for slide A is 1, but ref minus A for slide A is minus 1. Okay, so that's why A minus ref here becomes 1. Slide 1 has nothing to do with B minus ref, so that's 0. What will be slide 2? Slide 2, I think A minus ref will be minus 1, and B minus ref will be 0. Right? Slide 2. It's going to the direction of ref. So ref minus 1 is actually 1. So a minus ref is minus 1. That's why you have minus 1 there. And slide 3 has nothing to do with a minus ref, so that's 0. But b minus ref, yes, arrow going to the direction of b, so b minus ref is 1. So I hope I don't know how else to explain, but I hope you got the idea of the direction of the arrow. When something becomes 1, when something becomes minus 1, when something remains 0, what's on your rows and what's on your column. Number of independent parameters versus number of experiments you have done. So that's your design matrix. This is called the design matrix. Okay. So in order to do in a matrix notation, what you actually do, you actually bring those columns and you do a modeling, and then I'm slightly showing you that. So the columns, the independent parameters that you had, you can actually figure out what's the value of each gene in each slide by doing this modeling of your design matrix times your independent parameters. So that's the matrix notation. And how it works is, if you want, so the modeling is nothing but trying to estimate what is the expected value. So we are talking about a gene. So let's say gene Y. So what's the expected value of gene Y at slide 1, at slide 2, and slide 3? So you have 3 slides. So let's pick a gene Y. So you're trying to calculate the expected value of Y1, Y2, and Y3. And you can do that by first constructing a design matrix. And we already went through what 1, minus 1, and 0, 1 means, times your number of independent parameters. So independent parameters here is A and B. And then the way the matrix multiplication and other things work, so should you construct a matrix like that and multiply it by your independent parameters, so maybe you forgot linear algebra, I took it a long time ago, but that's how it works. So your rows get multiplied by your columns. So 1 times A plus 0 times B. So your final output value will be A. So that's what you're trying to do, right? You're trying to get the estimated value of your gene Y at slide 1, Y1. So your Y1 will be equal to A, your Y2 will be equal to minus A, and your Y3 will be equal to B. And that's how the matrix notation works, right? So rows, columns, and you can work through this example, and then you can finally see, yes, do you or do you not arrive to this A minus A's and B's. So that's simple. That's the modeling part that's going on in these slides. So as far as modeling data is concerned, so we had 3 slides, right? And so we are trying to figure out what's the magic equation, the magic model that tells me what are the values of my genes in each of these examples or experiments. So if you have 2 data points, it's very easy. It's determined. You can connect those 2 lines and you get a line. So that's your equation. So it's very simple. But real life, we're not only concerned about 2 data points. You have many data points across your experiments that you're trying to estimate. So you're trying to come up with a magic equation or a model that tells you that you can correctly estimate the value of the first experiment, second experiment, third experiment, fourth experiment. So if you could come up with the equation that would, a graph that would look kind of like that, like a linear regression, and most of you know that, I'm pretty sure what linear regression is, that's what we're trying to get it. So we're trying to estimate things by a linear regression. And in linear regression, what we do is, if that's my estimated line, which is in dotted lines, then how far I am, if that's the first thing that I propose, so each of these line, the bars, is how far I am from the actual data point, if that's the first thing I try to propose. So what you try to do is then you try to minimize these errors. And that's exactly what's going on. You want to minimize the sum of the square of these errors, the difference, and that's your linear regression. So that's what guides you. So you can have many lines that you can predict, but you will only pick that line, which is called the model fit, that minimizes your sum of the square error difference. So that's the best line. And that's exactly what's going on in your linear regression. The method of least square find, the line which minimizes the sum of square roots. Now, another way to look at it is, let's say you had an example where experiment where you treated someone with drug A, another sample was treated by drug B, another sample was treated by drug C. And then in this particular sample, maybe you had replicates, right? So let's say you have 6 replicates where it's treated by A, maybe 5 replicates treated by B, and 4 replicates treated by C. So in each of these cases, what you're trying to do is you're trying to estimate the mean value which will represent each of these sample type. Now, once you get the mean value of your initial condition, let's say that was A, then you redo the same experiment an hour later or 24 hours later. So initially it was A, then 24 hours later it becomes A prime. So if you've estimated your mean correctly for the first condition, which is A, then you again estimated your mean correctly for the second condition, which is A prime, then you can actually compare what's going on between 1 hour and 12 hours. And that's all you're trying to do by modeling. You estimate the mean correctly, then you compare, then you can say that yes, looks like when you treated something with drug A, and 24 hours later your mean went down. That means it was down-regulated. For your sample B that was treated with drug B, it was also down-regulated. But for your sample C, it was actually up-regulated because your mean went up. So that's the fundamental concept if you want to think about that. So linear models. Now, this one again goes through actually 4 samples. Initially we went through 3 samples. So you can also go through this slide. It will do the same thing. Instead of 3 samples, now you have 4 samples. And then because you have 4 samples, your number of independent parameters will be actually 3. Okay? But if you're comparing A minus B and B minus A, if you're comparing only 2 of them, then you're only interested with 1 parameter. So that's your independent parameter. So you have 4 samples, but what I'm trying to compare is only A with B and B with A. So if you have 2 comparisons that's needed, A with B and B with A, then you have to subtract 1 from it. So that means your independent parameter becomes 1. Then you design your matrix. So for A minus B, maybe it's plus 1, minus 1. For B minus A, it's plus 1, minus 1. So we'll figure out the pluses and minuses in the matrix. We'll show you. The slide shows you. Then it has to be multiplied by 1 parameter because you're doing 2 comparison. And that's what it does. So you have 2 samples here, A and B. Okay? But 4 arrays. So your number of independent parameters, as I told you, will be number of samples minus 1. So your independent parameter is 1. In the reference A and B diagram that I showed you, you have 3 samples. So your number of independent parameters needed to be 2. Here you have 2 samples, so your number of independent parameters will be 1. So if you're comparing B with A, right, so on this scenario, it will be minus 1 because it's going towards the direction of A. So A minus B is 1, so B minus A is 1. Sorry, A minus B is 1, so B minus A is minus 1. So that's why the first array gives you minus 1. The second one is B minus A going towards the direction of B, so that's 1. The third array, B minus A, again is minus 1, and the fourth array is 1. So that's how you put the minuses and pluses for your 4 experiments. You had 2 samples, so you needed a 1 parameter. So that's your 1 parameter, B minus A. And so if you're trying to now model and you want to figure out that, pick a gene, and I want to write a model that tells me what's the value of that gene in any of my samples. So that's your expected values. That's how you'll design your experiment, which is X. Your coefficient beta, which is your independent parameter, will be B minus A. And that's your end value that you will get for each of your genes. So that's the concept in plain man's term or layman's term, you know, what the modeling linear model is. Again, so this is now 3 samples, right? So reference A and B. So your independent parameter will be 2. Okay, and then it also tells you about comparing A with B, A with R, or A with R and B with R. Okay. So 3 minus 1, right? So 2 parameters. So if you look into this in your matrix here, so that will be 2 parameters. So that's that, A minus R and A minus B. And if you're comparing A minus R here, right? So it's arrow going towards the direction of A. So that will be 1 here. but A minus B will be 0, right? A minus B is 0 because in this first experiment, so each of these line again is experiment. So arrow going to the direction of A, so A minus 1 is 1, and A minus B is 0, and then minus 1, 0, 1 minus 1, minus 1, 1. And then you can actually do that by some algebra and try to think of it, whether these minus 1s and 0s are making sense or not. And when you do your LIMMA package, this is the critical thinking that you need to do. No, out of these conditions, what value? If you do not draw your design matrix correctly, and if you do not do your contrast matrix correctly, your experiment is not going to work out. So it's very important that you understand that. Then contrast matrix talks about is how many ways you want to compare, right? So if you have an initial model, how you modeled your expression values was like this was the design matrix, and that was your number of independent parameters. But now if you want to compare A with B, then B with A, and you want to tell me what A plus B, if I want to compare the value of A plus B and divide it by 2, just an example, maybe not relevant for gene expression, but if that's what you want to do, you want to compare A with B and B with A, and A plus B by 2, so that's how you'll use your contrast matrix. So this is A minus B, B minus A. So this is A, B, A minus B, and this is half of A and B. So, right? So that's your contrast matrix. And we will do the time series lab, where it will make more sense when I'm comparing between time point A or time point B or time point B with time point C. That helps me to design the contrast matrix. It will be better said by an example. The design matrix, you have to understand why something is 1 or minus 1 or 0. But again, and the last point here is, I don't want to say, you can already see how complicated a two-color array can get with factorial and whatnot, and interactions and trend analysis. We're not getting into those. This class is very easy, by the way. So the last thing I wanted to cover is for the FA matrix array. It's very simple. So follow this slide. So the FA matrix array, what it's doing is you have 4 FA matrix array, and under each of this array you have for sample A 3 replicates, sample B 3 replicates, sample C 2 replicates, and sample D 2 replicates. So the beauty of FA matrix array is the number of independent parameters is equal to number of arrays. So how you would lay out, so if you did an experiment like that with 10 FA matrix array with 4 different sample types, so since you have 4 sample times, what goes here is the number of parameters. So you just lay out the 4 parameters. Very simple. The number of sample types, right, is equal to number of parameters. And I think my dim just cut out, so I'm going to close out, and I'm recording it, so I'll upload it. And then for the X, wherever your sample A is present in the first 3 arrays, so Y1, Y2, Y3 will be all 1s, has nothing to do with B, so it will be all 0. Then you will have on the second column is your B, so 3, 1 populates on your second column. 2, 1 should populate for your third column, which is C, and rest is 0. And 2, 1 should populate for your column D, so that's your 1s. And that's how you construct a design matrix for FA matrix. So remember two things of the array. So your number of parameters, number of samples, and in this case under A you had 3 of them, so 3 1s there. Second one will be 3 1s. So you can actually follow very easily what's here between what's in your design matrix. So design matrix is easy for FA matrix array. And contrast matrix is nothing but how you want to compare. So if you want to compare A with B and with A with C, right? So if I want to compare A with B, so for the first 2 column it will be 1 and B is minus 1. And my third and fourth column, which represents array type C and D, has nothing to do with A and B. So in my contrast matrix, it will be zeros. And now if I want to compare A with C, so yes, A, so that's 1. Has nothing to do with B, so that's 0. Yes, it has to do with C because it's A minus C, so that's minus 1, and D will be 0. Very simple. So when you're comparing A with B and A with C, that's how initially I would construct my contrast matrix. So that's pretty much it. It's 6:45, and I think the dim session timed out, so I'm just going to record it and upload it, and you guys have a great Thanksgiving weekend.